Hello again everyone, welcome back to ptet.chemistry channel. This is the start of the section B on topic 8, which is my classification for chemical equilibrium. All those things with Kc, Kp, Le Chatelier, well, you know what I'm saying, alright? So with this section B kind of question, so if 1, 2, and 3 are correct, there's option A. If 1 and 2 are correct, there's option B. 2 and 3 are correct, there's option C. And if only 1 is correct, is option D. People who are familiar with Cambridge International paper 1 who have been familiar with these. However, I've seen these type of questions appearing more and more often in the other UK level as well as other 16 to 18 years old examination elsewhere in the world, because they do assess they're pretty good at assessing students' capability across multiple concepts instead of just testing one thing. If we go straight into this first question, this is a graph of Kp against temperature. So what you can see is as temperature increase, Kp increase. That is the first conclusion. As temperature increase, Kp increase. So your equilibrium shift to the right. You get more Z, you get lesser of X and Y. Equilibrium shift to the right, favor forward reaction. Favor forward reaction. Okay. So what can we say from this? What can we say from this? At higher pressure, equilibrium mixture, what are we talking about? At a higher pressure, equilibrium mixture contain a greater proportion of Z. We can also be thinking about there's 1 mole of it here and 1 mole of it there and 1 mole of it. This is a gaseous, and gaseous. So we talk about 2 moles of gas on the left hand side, which you need to write out in full in a theory paper. 1 mole of gaseous product on the right hand side of the equilibrium. So when you increase pressure, the equilibrium will try to oppose the change by decreasing the pressure. And because you have 2 moles of gas here and 1 mole of gas here, the equilibrium will try to decrease the pressure by shifting to the side with lesser gaseous molecule, which is to the right. So higher pressure, equilibrium shift to the right hand side to try and decrease the pressure, because the right hand side is the side with lesser gaseous molecules. Okay, so indeed you will get more of Z, okay, at higher pressure. How about if we think about the temperature? Okay, so this is what happened when as Kp is related to temperature. So if this is true, if we say the reaction is exothermic in the forward direction, or we say the forward reaction is exothermic, then when temperature increase, that means the system will try to decrease the temperature. So what will the system do? The system probably should get my grammar correct actually. The system tries to decrease temperature, but what does your system do? Your system release heat. So when you want to decrease temperature, you will by releasing less heat, because that's all it knows how to do. Whether you release more heat or less heat, because you are exothermic. You want to decrease temperature, you release less heat, and when you release less heat, you will favor the left hand side of the equilibrium. So equilibrium shift to the left. Shift to the left hand side. And what do we notice? We said as temperature increase, Kp increase, equilibrium shift to the right. So that means option 1 is incorrect. 2 is correct, 1 is incorrect. You can only be option C. That is 2 and 3 are correct. Okay. If we look at check option C, at a higher temperature, you have more Z. At higher temperature, Kp increase, equilibrium shift to the right. You favor forward reaction, you have more of Z. So number 3 is also correct if I check it also. Okay. Moving on to the next question. So this is basically just background information on what this question is about, but the equilibrium reaction is the key here. The forward reaction is endothermic. You see there's a positive enthalpy change sign there. At a lower temperature, so what we will say is the forward reaction is endothermic. So all it knows how to absorb heat. Okay, so as you decrease temperature at a lower temperature, the system will try to oppose this by increasing temperature. how would an endothermic reaction increase temperature? Endothermic reaction absorb heat. If you want to increase the temperature, therefore the system will absorb less heat, because if you absorb more heat, then your temperature would increase. Okay, hang on, let me just get this right. As temperature decrease, this is your surrounding, and your system is your reaction. Your reaction will try to oppose this change. Your reaction wants the temperature to increase. Okay, your reaction wants the temperature to increase, and therefore you absorb less heat. Okay, that's correct. Okay, when you absorb less heat, your equilibrium will shift to the left. You see, it's very easy to get confused, right? So you need to be aware of what is the system and what will the surrounding, what is the surrounding. Okay, so equilibrium shift to the left, and equilibrium shift to the left. So 2 is correct. How about what do they want? Why the forward reaction is more likely to occur at higher temperature? So it doesn't quite like low temperature. It likes high temperature because it doesn't happen at low temperature. So high activation energy is precisely correct. So slow reaction. So it's about slow reaction at low temperature. So it only occurs at high temperature. So when we talk about at high temperature, we can overcome the activation energy. We can overcome the equilibrium position. It will shift to the right because the forward reaction is endothermic. But it's saying that hydrogen and carbon monoxide do not react at high temperature. That is incorrect because you have equilibrium. So that means for as long as you're in equilibrium, you do not get 100% conversion this way. You always get a little bit going this way as well. So they do react because they are in equilibrium, they are reversible. It's just the extent of the equilibrium. You are shifting it more to the right, but you are not totally going to the right because this is still in equilibrium. So 1 is incorrect, only 2 and 3 are correct. This next question is your case study, even from your O-level or GCSE, to do with, I'm not sure if this is in GCSE, but sulfur chemistry is in O-level. So the only reversible step in the contact process is the SO2 going to SO3. That is a gas, gas, and gas. Don't forget to balance the equation. All right. So which process involves the conversion of sulfur dioxide into sulfur trioxide? Well, contact process does. Okay. If I check number one is if you have a sulfur contaminated carbonaceous fuels referred to hydrocarbon. So just basic, well, not necessarily hydrocarbon, but mostly it's just the hydrocarbon fuel, but it's contaminated with sulfur. Then you can have sulfur burns in oxygen to give you SO2. The sulfur in the sulfur contaminated fuel. Okay, so balance equation. That does not involve sulfur dioxide going to sulfur trioxide. So 1 is wrong. Since number 2 is correct, 1 is wrong. Definitely the answer is C. But number 3 is part of inorganic nitrogen chemistry, which you will see in topic 9.4 in my classification. This involves environmental chemistry, okay, which are very often asked in AS level chemistry as well. Okay, so you got to know about the reaction that goes there. Yeah, this is number 2 is what you call man-made in industry. Okay, number 3 is nature production of H2SO4, which is your acid rain. This is the man-made H2SO4 for use in industry. Okay, so I'm going to show you what happened here, which you can find out more in topic 9.4 under the theory section as well. So what happened is your NO2 plus the SO2, it will catalyze the formation of SO2 going to SO3, not reversible because we are not in man-made condition, we are in upper atmosphere. This oxidizes the SO2 to SO3. Itself is reduced. This equation is balanced. But I talk about catalysis. This is catalyzing the oxidation SO2 to SO3 in atmosphere. The NO can react with more oxygen in the atmosphere to give you back the NO2. So the NO2 is not used up at all, it's regenerated. This happens in the atmosphere. That's why I said it's part of environmental chemistry as part of the AS level, inorganic nitrogen chemistry. Yeah. So indeed you do get SO2 going to SO3, and that's what I meant by catalytic there. Okay, but just by checking 2, just by knowing that 1 is wrong, then you could have gotten the answer and move on. In this next question is another part of your case study. This is called Haber Process, which is the production of ammonia in industry. Which statements are true of the commercial process? Yeah, it's kind of like just a condition really. So you do need high pressure, you do need temperature, but you don't need that high. Typically we use 400 to 500 degrees Celsius. 1000 is too high. Okay, so 2 is correct, 1 is wrong. There can only be one answer. The reason, okay, why this? Why not higher? Okay, they love to ask you that. Surely higher temperature will mean faster reaction, right? Because you can break the nitrogen triple bond. Yes, but then you also have equilibrium, and the forward reaction is exothermic. So your forward reaction is exothermic. These are all part of equilibrium stuff which you learn from O level. Your forward reaction is exothermic at a very, very high temperature. At very high temperature, what would your system do? Your system, which is your equilibrium, which is your reaction, will try to decrease the temperature. It will try to release less heat. Release less heat means produce less ammonia, because it will shift to the left. Produce less ammonia is not good for you. So you don't want very high temperature. But at the same time, you don't want too low temperature, because the reaction will be very slow. Okay, because the nitrogen triple bond are very strong, very high activation energy. Yeah? And we know that the yellow ammonia is pretty bad. That's why we recycle. We recycle the N2 and H2. Okay, think about the setup. Sometimes they do ask you to draw a simple setup of how the Haber process works in industry. Sometimes they give you the setup. They ask you to think about labeling the setup in industry. Okay, so you do recycle the N2 and the H2, which was obtained from, this is obtained from liquid distillation. Sorry, not liquid distillation, distillation of liquid A, and this is obtained from usually cracking of hydrocarbons. All right. This is the last question of this section B question on chemical equilibrium. So in this question, I guess it's a lot of playing around with the words. So you have 2 experiments, and both of them produce R, and you measure them against time. So both of them involve this reaction. It's just using different catalysts. As you can see, the experiment 1 has a, I hope you can see the experiment 1 has a more, hang on, I'm trying to show it to you that experiment 1 has a steeper gradient of the change in the amount of R over time. So experiment 1 is faster. As you can see, it's steeper than the slope for experiment 2. Okay, that means they have different rate. Experiment 1 is faster than experiment 2. Okay, what else can I say? Here is just a moment in time. They do not tell you that the reaction is complete or not. Okay, so experiment 2 is just using a different catalyst, and as you know, catalyst using different catalyst does not affect the amount of product. So catalyst does not affect how much equilibrium product you get. It simply affects how fast you reach equilibrium. Okay, so always a very confusing question. Yeah. So when you use a different catalyst, yes, you can get a different rate. It's not saying that a catalyst give you different amount because they never tell you the reaction is finished for experiment 2, because experiment 2 could keep on going, and it should by right give you the same amount of R at the end of the reaction. They never say this is the end of the reaction for experiment 2. They just say at a moment in time. But of course experiment 1 has ended a bit faster than experiment 2 because there's no more change in the amount of R. Okay, so less of P was used. How do I say this? We could see from the diagram experiment 2 is simply slower than experiment 1. Okay, so when you use lesser P, you should still get, how do I say this? When you use lesser P, since the system is in equilibrium, you can still get the same amount of R eventually, but obviously the amount of R is a bit lower. So we're talking about the amount of R is a bit lower. So you can tell if you cut this moment in time, there is lesser R at the same time. Okay, we could relate that to experiment 2 being slower than experiment 1. Okay, but that could be down to a different catalyst. But there's just one of the suggestion. But it could also be down to less of P was used. You are in equilibrium. If you use lesser P, then the concentration of P decrease. Then equilibrium will try to increase your concentration of P, because that is what Le Chatelier's principle is, to oppose the change. And therefore equilibrium shift to the left hand side. You favor the backward reaction, you form lesser R. Okay, so forms lesser of R. Okay, so you get lesser R at a unit time compared to experiment 1, but it doesn't mean that you won't get the same amount of R at the end of the reaction. Okay, if you use a different catalyst, but this is not talking about catalyst, it's saying less of P was used, so you get lesser R as a result of the equilibrium position shifting since you are in equilibrium. Le Chatelier principle. So this question is a bit confusing. Yeah, these are different conditions, okay, that can explain the result. Product S was continuously removed from the reaction vessel. So S is a product. If you remove S, removing S would mean the concentration of S would go down. If the concentration of S would go down, it's kind of like this thing where we talked about before. What would the equilibrium do? Equilibrium would try to increase the concentration of S, and therefore to increase the concentration of S, the equilibrium will shift to the right. Okay, so equilibrium shift to the right, and when you shift the equilibrium to the right, you will get more of R per unit time. You will expect the rate of reaction to be faster. Okay, and it's the opposite of this. Okay, so forms more R. Therefore, you expect the concentration of R to increase, the amount of R to increase, and you wouldn't expect it to be slower, you expect it to be faster instead, okay? Because you're changing from experiment 1 to experiment 2, okay? So if we do that, then we will expect it to be faster than experiment 1, which it isn't. It is slower than experiment 1, okay? What I mean is it's slower in the sense that at a unit time, you get lesser R compared to experiment 1, and this will give you more R at that unit time as a result of the shift in equilibrium position. In reality, it's about Le Chatelier principle. It's about a catalyst can give you a different rate of reaction, okay? But it doesn't tell you that the reaction is complete here. Experiment 2 should by right give you the same amount of product if this is the only change, because a catalyst does not affect the amount of the product form, but changing the concentration can affect the amount of product form at equilibrium. So the only correct option would have been option B. Okay, this is the end of this 5-question tutorial. I hope that helps. If you think this channel is helpful, please do subscribe to the channel and share the words to your friends, your class group chat, your anyone else you know who might benefit from this channel. Thank you for watching.